In this block sliding problem, we start with a block which is on a horizontal surface which has friction on it. And the block initially starts out moving to the right at 6 meters per second. And after it's moved 10.2 meters, it's now going 2 meters per second. And the mass of the block is 2.04 kilograms. And we're asked what's the kinetic coefficient of friction, and then part B, what's the average power loss during this time. So I'll pause right now, solve the problem, and then we'll compare the answers. So for part A, I got this kinetic coefficient of friction is 0.16, and the average power loss is 12.8 watts during this time. So here's the solution path that I chose. So I chose to use an energy balance. One could have used Newton's second law equations and constant acceleration, which we'll find that that's what is actually what this case will be, and solve for these values as well. Energy balance is a parallel thing to do, and that's the method I chose to solve this with. So using energy balance, what we're going to say is the sum of all the kinetic energies at the final stage plus the sum of potential energies due to gravity, the final stage, plus the sum of all potential energy due to springs, final, equals the sum of kinetic energy, potential energy, and spring energy, all parts at the beginning, plus the non-conservative work that's done. Now in this problem, it's horizontal. We have no springs, so a lot of these potential energy terms all go to zero. And we only have one mass moving. There's the same mass moving from there to there. So I don't have multiple masses with multiple kinetic energies. So it just turns out to be the kinetic energy, the final of that single mass, is kinetic energy initial plus the non-conservative work. And so if I solve for non-conservative work, so that's the final minus initial kinetic energy. Kinetic energy is mass times magnitude of velocity final squared minus this term with initial velocity squared. It's a scalar quantity. And the work non-conservative is the forces acting on the part times the distance. So we don't quite know what that is yet. Well, times the angle between the motion and the force. So we don't know what that force is yet. So we'll have to figure out how I get that force that's acting. So to do that, one method is to do a free body diagram. If we do that of the block, so here's my block. So and what do I know? I know it's changing velocity here. It's different velocity here than here. So in this horizontal direction, acceleration is taking place. So that's a sub x. There was no acceleration up or down, so there's no acceleration here. Forces, I have gravitational force pulling down. I have a reaction force perpendicular to the surface here, which is acting straight up and down here, and I have a friction force. And since I know I'm sliding, is what I was told, my friction force is going to be my kinetic coefficient of friction times the normal force. So that's only true because I was told it was sliding. And now picking a coordinate system, you want to pick one in the direction that you have some information on accelerations. Well, I know this acceleration here is 0, so I want to pick that one, and then it's moving this way accelerating, so that's a good coordinate system. Now, positive x is this direction, so sum of forces positive x is mass times whatever acceleration I have in the next direction. And now the forces, I only have this frictional force, which is acting in a minus x direction. And we know the frictional force is since I'm sliding, is the normal force times the kinetic coefficient of friction. Now sum of forces in the positive y direction, positive, is mass times acceleration y, which I know is 0. It's not moving up or down. And all the forces, I have a positive normal force and minus m sub g. So if I solve for this equation, I know that the normal force is m sub g in this case, and the frictional force is mu sub k, the normal force. So frictional force is friction coefficient times mg. So here I know the magnitude of that frictional force. And mu sub k is a constant, m is a constant, and g is a constant. So during this entire motion, we know that this force that's acting here is a constant. Okay, and we know it's acting in this direction. Okay, and we know that the motion is going in this direction. Okay, so I know that's a constant. So I can just say that's my constant value here, because I'm not changing. If the force is changing over time, I need to do this integral. But since it's a constant, it makes it much easier. So it's the force times the distance. That's the work. And since the force is acting in this direction, and the motion is acting in this direction, the angle between the force and the motion is 180 degrees. So the cosine of 180 degrees is -1. So we know that this force is negative. It's the non-conservative work is negative. So here's my non-conservative work. It's minus this constant force times the distance. Well, I know I just solved here that the frictional force is mu sub k mg, so I can substitute mu sub k mg here for frictional times distance. Okay, so if I then just solve for this, okay, so this is my mu sub k mgd. That's that value right here, and that's that work right here. Is this difference in kinetic energy, which is right here, and you can see that I got m terms in both of them. Okay, so I can m can cross out, and if I simply solve for mu sub k, I get minus the final velocity squared minus initial velocity squared over 2gd. Okay, so if I just put in numbers here, I get mu sub k minus this term right here, 2g, and distance traveled. You can see units cross out. So mu sub k is 0.61. So that's the answer to my first part of the problem. Second part of the problem, we know that power was the question. What question is power? So power is the change in energy over the change in time. So we don't know yet anything. We know something about the change in energy, because we know the initial and the final velocity. So I know that term. That's my change in energy, but I don't know what my time is. So there's many ways to try to do this to figure out what time it is. One way to find out is just to use the fact that if I back to my free body diagram on this sum of force equation in the x direction, mass times acceleration x direction is minus mu sub k mg, this frictional force. Okay, and then m's cross out, and since now I have that kinetic coefficient of friction, I know a sub x is minus kinetic coefficient times g. So there's my acceleration rate, and it's decelerating in that positive x direction, and that's the value. If I want to know the time, since this is a constant number, mu sub k is constant, g is constant, we have a constant deceleration. So if I think about the velocity versus time chart, I started out at time 0 of 6 meters per second, and then at some later time I was at 2 meters per second, and there was a constant deceleration taking place there. So it's just a slope line formula. So my final velocity equals initial velocity plus acceleration x over time. If I solve for time right here, I know my velocities, I know my acceleration. I can get time is 2.55 seconds. So now I know the time that it took from get to there. There's many other methods to get that, but this is one way to do it. I mean, one could have just used some of the equations we learned on constant acceleration just as well to get that time, rather than going through here. So now we think about power, change in power. So change in power is change in energy over change in time. So there's my change in my kinetic energy. I didn't have any potential energy effects. So that's this, my change in time right here. So if I put power, so just using this equation here, my mass now is important. I need that. My velocity difference squared. My change in time, and now I need to do some units conversions. I know that a Newton is a kilogram meter per second squared, and a joule is a Newton meter, and a watt is a joule per second. So you can see that I essentially I can do my check here. There's go good kilograms. I got meter squared here. I have a meter there and a meter there, so that's good. I have second squared and seconds here. So there's my second squared, seconds. I got my second, okay, and there's my joule and joule. So, and there's my Newton and my Newton. So therefore, you can see it makes all sense. I get it with watts. So if I put the number in there and solve, I've had an average power of minus 12.8 watts. And it's negative, which makes sense because I had a power loss, because I lost energy going from that state to this state.